All right, thanks, Corey, for the introduction. So this talk builds on a little bit of some of the stuff I presented last year at this session. We've teamed up with a group at Akron University, being used a group to do a tissue phantom study. So I'll be doing a comparison with their system, describe that in this talk. So first I'll introduce smartphone spectroscopy, just kind of what that means, go through that briefly. Go through a characterization of our Toptics smartphone spectrometer, and then discuss the setup for the tissue phantom study with the Akron system and our system, and then go discuss the results from the phantom measurements, the comparison, and then some conclusions and summary. So smartphone spectroscopy, what does that mean? So you can take a smartphone and combine it with an optical spectrometer. Okay, we can do that. All right, so here's our prototype. There we go. But this means a little bit more than this. By combining with a smartphone, you get really access to this big data analysis capability where you can incorporate, if you have these devices out, you can, in many locations, you can start to build up a large database and run very sophisticated algorithms both in the cloud to realize applications that really previously were unrealizable, maybe in the lab or with just a traditional setup in the field. So it's huge power capability there. Of course, the ease of use with a spectrometer, you can design any app interface for particular applications. It's a very simple operation, potentially. A minimal expertise required. I kind of rescind this experts feeling around spectrometers. And then, of course, portable and low cost. Any system that's going to work with a smartphone is going to be needs to be relatively low cost and portable, and this enables the capability to use it really anytime, anywhere. So how are we doing this? We've come up with a design. It was originally developed at Penn State to transform the traditional spectrometer configuration into a simplified setup with it's called a G-Fresnel that combines the dispersion, the focusing, and collimation properties of the traditional optics that are used in a spectrometer, all into a single element, where this can be made fairly compact and maintain pretty decent performance. And this design was recently patented. And Toptics has taken this design and created a very small miniaturized version of the Toptics spectrograph, kind of on the size of a penny. So this has gone through some lineage of development. Like I said, it was originally developed at Penn State, where the device was first described and the optical properties associated with it in conjunction with some fabrication techniques back in 2010. And then the group also demonstrated a spectrometer design using the G-Fresnel and demonstrated pretty decent resolution performance, less than 1 nanometer. And also, this paper describes how to develop a very compact G-Fresnel design. And more recently, the G-Fresnel was integrated with a smartphone by utilizing the back camera in a very simple design here in a Lab on a Chip article. You can kind of see how it comes together connected to an HTC smartphone. And this was shown or demonstrated for various absorption measurements and applications associated with that. So from a Toptics perspective, we're developing this spectrometer platform for integration with smartphones, wearables, other mobile devices. Also looking at the opportunity to develop some sort of OEM device around this spectrograph that we've developed. And primarily we're focused on applications in mobile health and fitness, application developments in this arena, and then also in agriculture and plant health. But today I'm just going to focus on brief applications here in relation to hemoglobin detection. So in relation to that, we're developing applications for non-invasive hemoglobin measurement. The clinical applications around this are well demonstrated for being able to rapidly assess blood loss in the battlefield, surgery arenas, car accidents, trauma patients, that sort of thing. And then the applicability for such a small, low-cost design and this non-invasive aspect really could be useful in low resource settings. They don't have access to the more sophisticated diagnostic equipment for particular applications for anemia screening and cancer screenings, both of which have been demonstrated using similar approaches. And then also there's some non-diagnostic applications for fitness and wellness. There's been a couple companies that have developed some applications around this for the ability to get a better sense of the body's oxygen carrying capability. Hemoglobin can provide that in a better fashion than maybe a typical tissue oximeter measurement. And then in particular, the applications that are being discussed around this are for high performance fitness training for athletes, for being able to improve recovery time, train harder, train faster, that sort of thing. So I'll get into our prototype that we use for the hemoglobin measurements I'll show later here. This is the prototype design working with it. It just attaches to the phone. I have a newer version up here that incorporates some other capabilities, but essentially this one's a fiber couple design. You can see the spectrograph here, and then these are just electronics that interface. These are specifications that we've come up with through some characterization of the device. So we wanted to get a baseline of how this system would perform and what we were dealing with in relation to the Akron system. So just go through some of the characterization we did. We figured out the spectral bandwidth and the spectral response for the system by using a monochromator and stepping through with known intensities for 50 nanometer increments. So we developed the spectral response for the system. Did a resolution characterization across that region using a mercury argon lamp. In this particular design, we kind of set it up to have about a 5 nanometer resolution across the full spectrum. And then wanted to make sure that the system responded linearly at the low intensity and close to saturation as we increase the integration. And we were able to show that the detector works well across the whole response of the detector. And then looked at the detectable limits. We had a limitation. We can only go down in this particular fashion to 2.3 nanowatts, but you can see, we could probably go a little bit lower and still be above the noise floor. And then before saturation, can measure up to 935 nanowatts at 600 nanometers. So we use those to derive these specifications for the system. So next I'll talk about the phantom study. And first, brief introduction to diffuse reflectance spectroscopy, what we use as our measurement technique. And then what diffuse DRS enables is the ability to look below through the epithelial tissue or top layer of the skin, essentially, and probe potentially, depending upon which wavelengths you're looking at, a couple millimeters. And we're not looking at the specular reflectance. We're looking at how the light either scatters or absorbs from the different organelles or cellular structure that exists here. And we can capture this reflectance spectrum, diffuse reflectance spectrum, which we then use we put it into an analytical or some sort of numerical model to extract out the key parameters for absorption and scattering, and these are what give us some sense of the hemoglobin. You can also get a beta carotene or melanin content, and then for scattering, you can actually you can deduce some information around the cell structure and so forth. So our experimental setup was to look at a side-by-side comparison of this University of Akron Smart DRS system and our DRS setup. So we created 16 tissue phantoms, nearly identical for each system. We titrated nearly identical concentrations for the tissue phantoms for each one, and then used the same Monte Carlo inverse model for extracting the absorption and scattering coefficients that we're interested in to characterize the tissue phantom. And this technique has been used, developed through Bing Yu's group in conjunction with some of his collaborators. So the phantoms were set up to mimic typical concentrations for hemoglobin. So 16 phantoms with the variable concentration here. The hemoglobin concentration, we started off with like an initial characterized concentration of the hemoglobin, and then titrated from that so we could deduce out what the concentrations were. And then the samples, the tissue phantoms had 1 micron polystyrene microspheres to mimic the scattering properties of tissue. So we could, knowing the parameters around this, we could calculate what the expected scattering coefficients were for each of the phantoms. So the University of Akron system, there's a reason why it's called SMART. It incorporates, it's not just a spectrometer with a light source, it incorporates a lot of nice improvements to the system, a method for doing self-referencing, which can remove, can account for some of the issues with the spectral source, the light source varying measurement to measurement, and also fiber bending and those sort of things for the system. And then also they incorporate a pressure sensor to find out the optimal pressure on a tissue sample. This I think it was used in some fashion for this work, but it wasn't as critical because we were just looking at water-based phantoms. And you can see the setup here for the Akron system. They use an Avante's 3-channel spectrometer, and this probe was custom built, incorporating these things here. Yeah, and just a little bit more detail on their self-referencing and pressure sensor. I won't go into detail on this. It's all discussed in this paper here. But they've demonstrated clinical applicability or usability with this system, where they can achieve absorption coefficient errors and scattering coefficient errors, on the order of these values. So they've used this in clinical settings. In one remote clinical setting, and have had some promising results from that. So versus that system, our system is fairly simple. We have just a separate broadband lamp source, our smartphone spectrometer coupled to a fiber bundle where the broadband lamp emits out of 6 illumination fibers, and we receive from the center fiber to perform diffuse reflectance. And you can see this is actually similar to the setup that they employ here. The fiber separation was around 430 microns. This is critical for determining the coefficients for using our extraction algorithm, having to know the separation for the diffuse reflectance probe. And both setups had a stirrer to make sure the measurement or the phantoms were well mixed between titrations for each phantom creation. So the measurement results. This is the recorded DRS spectra from our system for all the concentrations, and this is after using a calibrated reference puck to account for the spectral shape of the lamp source. So we divide through by that. But this, in comparison to the Akron system, this is not built in. This is just something we do after each measurement. So it's not so there's some issues associated with that. But you can see some of the characteristic absorption bands, Sorey band and the alpha and beta bands for hemoglobin. This is the expected versus extracted results for the absorption coefficients and scattering coefficients for our setup. You can see there for kind of medium concentration levels, they compare relatively well. It's on the extremes for low concentrations and high concentrations. There's some deviation for each. In comparison to the Akron system, these compare much more favorably at low concentration, high concentration. This is illustrated a little bit better in these plots here that compare the extracted versus expected absorption coefficients for each system. And then this red line here is the perfect agreement for each. And similarly here. So the errors associated with our technique versus the University of Akron system, you can see that they were able to achieve similar results to what's been previously demonstrated, doing this side-by-side comparison. Ours, the mean error is a little bit higher, but I think this is pretty exciting, pretty promising for such a, using a spectrometer like this little guy versus a large benchtop system. So we're pretty motivated by these results. In conclusion, this shows pretty decent feasibility for such a system to have a compact hemoglobin sensor that connects to a smartphone. Pretty exciting stuff. For future developments, we want to seek to get down to less than 5% measurement error, somewhere around this order, similar to the Akron system, by incorporating a more efficient optic that we've recently developed, and then also some improvements to the software, and possibly incorporating a self-referencing method. So working on this prototype that will incorporate all this. We're also looking at the applications for such a system that performs at these levels for some of these fitness and athletic applications that I mentioned briefly. So that's it.